I guess we can go ahead and start class. Today is the last lecture. No worries. Today is the last lecture, and next time we meet is going to be on the final exam day, which is May 4th. I don't remember the exact time. Was it 3 p.m., 2 p.m.? Maybe I said it in the previous lecture, so 4 p.m., huh? Yeah, so it is May 4th, 4 p.m. Is it a Thursday or a Tuesday? Yeah, let's see what the day May 4th is. Calendar. May 4th it's a Tuesday. Yeah. So in essentially it's gonna be in 11 days, 12 days, right? 12 days. And the exam, we talked about the final exam a little bit during the previous lecture. The exam is going to essentially cover a lot of basically all of the material we have touched on in this chapter. What you have right now in front of you, and by the way, if you haven't picked up one of these, make sure to come pick some up here in front of the class. What you have in front of you is the review of chapters 1, 2, 3, 7, and 8. There are a couple of example problems from chapter 3 and chapter 8. And what you should do to practice more is to go back to your homework. There will be a homework posted. Your last homework will be posted tonight, okay? And you will have time until next Thursday to submit it. So you will have a week to submit it. It will be a short homework, just 4 questions from chapter 7 to the Buckingham Pi theorem, and 3 questions from chapter 8, pi flow. And to have a successful final exam, to be successful in your final exam, you have to go back to your homeworks. Make sure to understand all of the problems that was given to you on your homework. It is not a bad idea to go back to your the review problems that I've posted, and we have worked throughout the semester to like work on those a little bit. Those problems are a little, I would say, except for the ones that are included in this handout, most of those problems are a little more complicated than what I would give you on an exam. So if you understand those, you should be fine on an exam, okay? And what else? Homework, make sure to study the lecture notes. There are 2 chapters, chapter 3 and chapter 8, that don't have a lecture note yet. I will make sure to post those this week. Pick up a handout right over there. Take your handout over there. Yeah. I will make sure those lecture notes are also posted before the weekend or during the weekend, so you have enough time to go over them. And the conceptual problems from chapter 5 and 7, I don't think we're going to have a conceptual problem from chapter 5 and 7, except for the one that I'm gonna mention. There will be one conceptual problem that I told you it will show up, and you will know what it is. So you will know what is going to hit you there. And other than that, there won't be any conceptual problems from chapter 5 and 7. Okay. Is there any questions so far? Okay. So what are the problems that are definitely going to be there on the exam? First and second problems, numerical problems, are one is going to be the Buckingham Pi theorem. It will definitely show up on the exam because a lot of people struggle on the Buckingham Pi theorem in the second exam. And the force balance, the use of momentum equation to calculate a force, anchoring force, or whatever type of force. That will also definitely show up on the final exam. So these two will definitely show up. So make sure to understand them. And what I'm going to do is to include one problem in the homework 5 for the use of the application of the momentum equation. So you'll get some practice there. But going back to exam 2 will give you, and also the examples we solve in class should give you enough material to work with. And the conceptual problems that will definitely show up is the conceptual problems that I have included here. And that is, what is the Navier-Stokes equation? And this is something we are going to talk about today. Yes. And the application of momentum equation in calculating the force, like the integral form of the momentum equation. And the conceptual problem that will definitely show up on the exam is one of the conceptual problems you have here. What is the Navier-Stokes equation? And I will explain I will answer this question in detail. And the reason I have included this is a very small part of chapter 6. And the reason I wanted to include this is because Navier-Stokes equations are the building blocks of fluid mechanics and the governing equations of fluid flow. It is not a bad idea for someone who is going out of this course to at least have some sort of exposure to these equations, right? No one really solves them analytically because, as you can see, these are very complicated equations, but you should have at least seen them, okay? And I'm telling you that these will show up on your exam, so make sure you understand them and know them. Okay, any other questions? No? Do you have any questions about the grades? Because I received some emails last night and during the week and weekend from some of you about the grades. Are we clear on what's going to happen with your grades? If you do well on your final, so there are a couple of things. It is not a bad idea to repeat this. If you have already done well on your exam 1 and exam 2, exam 1 and exam 2. Let's say you have received a B, or you have received a D and you are satisfied with your grade, right? You can send me an email and tell me that you don't want to take the final exam and you are satisfied with your grade. And that is perfectly acceptable to me, as long as you submit your final homework. Okay?
So if you have like an A in exam 1, 2, you can send a request after your final exam.
Yes, that's the idea. Because essentially what I'm doing for the people who have not done well in their previous 2 exams is that I'm going to drop. This is the least thing I'm going to do is to drop one of the exam grades, right, and replace it with your final exam. So it's only fair for this to go the other way as well. If you have done well in your first 2 exams, you should be rewarded. Or if you're only satisfied with your grade. B is a very good grade. C is also a very good grade. But if your grade is less than C, if you think your grade is going to be less than C, it is probably a good idea to take the final exam, because there are a couple of courses that are going to need a grade C or better in this course. Okay. And next thing, if you have done well in one of the exam 2, 1 or 2, one of them, and if you do well on your final, I will drop one of, I will replace, I'm going to replace your lowest grade with your highest grade. Doesn't really matter if you have done well or not done well. This is one thing I'm going to do, right? Let's say your exam 1 grade is 70, your exam 2 grade is 85, and your final exam grade is 82, right? I will replace your exam 1 grade with exam 2 grade, which is 85. And that applies to everyone in the class. Okay? And the third one is that if you have not done well in any of the exams, let's say your average grade is, I don't know, you have a failing grade, okay? But you have submitted all of your homeworks, you have come to all of the exams, you haven't missed anything, you have been through the class, and you get an A on your final. I will give you, depending on your grade and your average, I will give you a B or a B plus, right? Does this make sense? And there are a couple of people who have not participated, taken their exam 1 or 2, or have not submitted their homework. If you are in that group, and if you do very well on your final, if you get an A on your final, I will give you a C out of the course, right? So your final exam grade can actually change everything, right? And there are a couple of people who have progressed very well in the course, like from a very bad grade on exam 1 to a very good grade on exam 2. If you continue on your progress, you will definitely be rewarded, right? Is there any questions about the grades? No. Okay, so it is all clear, hopefully. And I want to say this before talking about all of the things that we have in front of you, and we'll move on. The last 15 minutes, this is the last thing I want to mention. The last 15 minutes of this class will be dedicated to your evaluation. And whoever submits their evaluation and send me the receipt will get a bonus point. There are a couple of you who have already done so, and I have, for most of you, for some of you, I have already updated your bonus points. For some of you, I haven't had the time yet. Also, if you have any more comments or feedback or whatever that you want to let me know, please include that in that email that you are forwarding to me, right? Okay. Any questions? No. Okay. So let's talk about, and this is what we're going to do today. I'm going to read through these problems, the conceptual problems. I'm going to read through these conceptual problems. I will ask for an answer. If you have the answer, you'll get a bonus point. If not, I will just give a brief answer and move on, okay? The same thing we did in the previous lecture. But I need to borrow a pen. Is there anyone who has an extra pen that can, or a pencil that I can borrow? I forgot to bring my own pen. Thank you. Thanks. Okay, so what are absolute and gauge pressures?
Absolute includes the atmospheric pressure as well as the pressure inside the tank. And gauge just whatever's inside the tank.
Okay. So essentially, your absolute pressure as compared to the vacuum pressure, this doesn't work. Can I get it? I'm sorry. Thank you. So absolute pressure, you compare your pressure with the vacuum pressure, which is essentially zero pressure. But the gauge pressure, you compare your pressure with the atmospheric pressure, right? So what is the gauge pressure of the regular atmosphere? The gauge pressure, that's the absolute. Zero, exactly. Okay, the next part is what is viscosity? Do we have any Takers here. Viscosity was essentially the heaviness of your fluid, right? I mean, in an exam, you have to explain it a little better, but I mean, how easy or hard it is for your a fluid and how it responds to the shear stress. The next part, next question, what are Newtonian fluids and what are non-Newtonian fluids? Do we remember this? Newtonian fluids were the fluids that had a linear relationship, right? Their shear stress had a linear relationship with viscosity, like this, right? These are the type of fluids we have. We talked about it in chapter 1, so they are already in the lecture notes. If you go back to lecture notes, you will see that this is this is there. So they have a linear relationship, and this is the relationship, right, between viscosity and shear stress. But we have non-Newtonian fluids that do not behave linearly. Like these are all non-Newtonian. I'm going to put non, that do not change linearly with the shear stress. Viscosity does not change linearly with the shear stress. And the examples of it are shear thinning, shear thickening fluids, and Bingham fluids. Bingham fluids, shear thinning, shear thickening. These are also in your notes. What is the vapor pressure?
When like the equilibrium is like condition is reached, the number of molecules leaving is equal to the number of molecules entering.
Equilibrium condition. So essentially that's exact. So if you have a closed door, if you have a fluid that in a closed door container, you will have a vapor pressure, vapor forming on top of that liquid. Essentially, when it reaches the equilibrium, that pressure of that vapor is called the vapor. What's your name? Hannah. Okay. What is pressure? And this is something that we will probably show up in some form or another on your exam, because a lot of you struggle with the concept of pressure. Anyone? Yeah. That's it. What kind of force, though? What's the direction of that force? Normal force, right? So your pressure, but you'll get the bonus anyway, so don't worry about it. Pressure is normal force per unit area. Let's say this is your force that you're applying to the surface. Pressure is going to be the normal projection of that force, the normal component of that force divided by your area, right? So pressure, normal force per unit area. And the next one is something we had on exam 1 as well. What does Pascal's law tell us? Yes.
Pressure is the same at one point in all directions.
Exactly. So at one point in a fluid, pressure is independent of direction, right? It's going to be the same. Ansley, right? I don't know how to spell your name, but okay. So what are the two types of forces in a fluid? I guess this is the question itself is a little vague. So let me just answer it. We have volume forces or body forces that apply to the whole volume, like weight, right? We also have pressure forces, right? Or shear forces that only apply to the surface of a fluid, right? Pressure only applies to the surface. Weight applies to the whole volume. So body forces and surface forces. What else? Define a free surface. Yes.
And not just like any fluid surface that's like open to the atmosphere.
That's it. That's any fluid surface that is open to the atmosphere. And on a free surface, pressure remains the same, right? That's actually a very important point as well. Write down your name as well. And there are a couple of topics that I want you to learn. Like, go back. We actually have a very extensive discussion on the lecture notes as well. We talked about it extensively in class 2 about the buoyancy, flotation, and stability. This was also in exam 1, and a lot of people struggled there. So just 3 pages on lecture notes. If you go back to the lecture notes, you will see 3 or 4 pages on lecture. If you go back to the lecture notes, you will definitely learn what is going on there. And this actually, there's a 90% chance this will show up on the exam as well. And we also have the static, dynamic, and total pressure. Is there anyone who can tell me what are static, dynamic, and total pressures? Do we remember these concepts?
Static pressure when it's at rest, or the fluid's at rest, and then dynamic pressure is obviously when it's moving, but it's some formula I don't remember.
So you said it the other way around. So a static pressure is the pressure you're going to feel when you sit on a moving particle of fluid. That particle can be moving or be at rest. Like the static pressure inside this room is 1 atmosphere. But the total pressure, not dynamic, the total pressure is the pressure you are going to feel if you bring down the velocity of a fluid particle to 0 isentropically, right? That was the definition of total pressure. And the dynamic pressure is the difference between the two. So total pressure is equals to a static pressure, or this is also called a stagnation pressure. Stagnation plus dynamic pressure, Q infinity. You can actually calculate Q infinity with 1/2 rho the infinity squared. And what was your name? No, yeah, I keep forgetting your name. So the next question, this is something that we need to talk about, is that what are the Navier-Stokes equations? So you are already familiar with the momentum equation and how we find them. Using the Reynolds transfer theorem, right? The idea was for a system was a selection in a space, right? With a 0 mass. Sigma F is that was the momentum equation from an integral perspective. It's called integral perspective, which essentially means that it has integrals in it. That's it. The d of linear momentum of the system dt, the total derivative, was equals to partial t of the rho v dv, right? That was the general form of the equation, which we barely use this general form, rarely, very rarely. Okay, so this is the momentum equation. Using this momentum equation, you can find the velocities, you can find the different characteristics of the flow, and so on and so forth. This is actually something that will definitely show up on your exam as a problem that you need to solve, right? But the Navier-Stokes equation comes from a partial perspective. So what is a partial perspective? So in an integral perspective, we applied this concept, this force balance, to a system. This system it can be very big. It can be the size of this room. It is not a very small element. That's the point. It can be small, but it's not considered a very small element in a fluid. But the partial perspective applies this force balance to the same idea, but to a very small element inside your fluid. This small element that I'm sure you have seen this small element a lot, has in Cartesian coordinate system, has the size of dx, dy, dz, right? So whenever you move to a differential, that's a differential or partial, whenever you move to a differential analysis to a very small element, you are going to have this partial or differential perspective. But how can we find a momentum equation for that perspective? We can actually apply the same idea here. That sigma f is going to be equal to total derivative of rho v with respect to time. And everything is divided by the volume. So I'm not going to go through the derivations, but that's the idea. So total derivative of this is going to be the partial rho v partial t, right? Plus velocity in your one direction. This actually is going to be v gel. That's the general definition multiplied by rho. But we can expand it to different directions. So we have three different directions, x, y, and z. Let's do the sigma f. Let's write this equation for the x direction. We're going to get partial rho u, partial t. Again, this is general form. Velocity in the x direction, partial rho u, partial x. Velocity in the v direction, partial rho v, partial x. Velocity in the z direction, partial rho. This is partial y, sorry, partial z, right? So this part is just an expansion of the total derivative, which you have already seen. We actually had an example of this on the exam. Okay, so this is the right-hand side of this equation. The left-hand side is the forces. We already know that the pressure forces always exist, right? We also have shear forces present here. And there's also the presence of your body force. So depending on the direction of the flow, we are going to have negative rho gx. Everything is divided by volume. So mg, your weight, is going to be rho gx plus the changes in pressure in the x direction, or minus, plus your shear in the x direction is equals to whatever that is over there, the right-hand side. From this part forward, the next simplification makes this equation, or the Navier-Stokes equation. The reason they call it Navier-Stokes equation is because it was developed by Navier and Stokes. This essentially gives you a simplification on how to calculate your shear stress. Your shear stress is going to be mu partial squared u partial x squared plus partial squared u partial y squared plus partial squared u partial z squared. And the same thing applies for the other directions. Okay, so Navier-Stokes equation is going to be negative rho gx plus the changes of pressure. It's actually minus m plus, sorry, plus the shear, which is this, is equals to this side. If I ask you to write the Navier-Stokes equation, this is the equation you have to present. And I assume you already heard the explanation. So it must be followed by explanation of what this equation represents, right? And this will be a question on your exam. That's 100%. I will ask you to give me the integral perspective of the momentum equation, the differential or partial perspective of the momentum equation, which is going to be this. And then I will ask you to write down the Navier-Stokes equation, which is this equation, and tell me what this Navier-Stokes equation represents, which is essentially the momentum equation, right? Just the application of the momentum equation in a very small element of the fluid. Okay? Do you have any questions? So let's move on with the problems. And whoever can answer these will get a bonus point. How do you calculate the Reynolds number? And why is it important in fluid mechanics? Yes.
The formula for the Reynolds number is density times velocity times diameter, all divided by the viscosity.
Exactly. Why is it important? Do you know that, the other part? It's a dimensionless parameter that distinguishes between the laminar and turbulent flow, right? So if you calculate the Reynolds number, we can essentially understand whether your flow is laminar or turbulent. Okay. In a pipe, your Reynolds number is calculated by rho v multiplied by diameter, but on a flat plate, you have to calculate the length of the plate, right, not the diameter. But whatever you give me in an exam is acceptable, right? The point is this length here for Reynolds number is a characteristic length, right? If diameter is the important thing in your analysis, whatever analysis is flow over a cylinder, right? That's also diameter is a very important what is it? The length there. So you should use diameter. So whatever that length, characteristic length is. What is the value, the transition? When does the transition to turbulent begin? At which Reynolds number in the pipe flow? These are values you have to have readily available. I mean, you have to memorize this. In a internal flow or a flow inside a pipe or a pipe flow, transition happens at Reynolds number of 2100 to 2300. That's the beauty of Reynolds number. We don't need to know the type of liquid, type of pipe, just need to know this Reynolds number. If you can calculate it for a specific type of flow, you can say whether it's laminar, turbulent, or in transition. Okay, Cooper. 2. What is the difference between laminar and turbulent flow? Okay, exactly. So laminar is not necessarily uniform velocity, but it is orderly, right? What does this mean? In a laminar flow, a uniform velocity, let's say this is your pipe, a uniform velocity means your velocity is uniform, the same everywhere. In a laminar flow, you can actually have this type of distribution of velocity. But the point is the velocity here is going to remain the same over a span of time, right? It will always be like 2 meters per second, right? 2 feet per second, whatever, right? But in a turbulent flow, you will have a lot of fluctuations. You will have a lot of vortices. You will have a lot of mixing happening, right? Which you don't see in a laminar flow. Okay. What is the entrance length in pipe flow, and how do you calculate it? Anyone remember? Okay. Entrance length, if you recall, the idea was you have anyone? No. If you recall, the idea was that, let's say this is your pipe. Flow outside of the pipe is uniform at V infinity, right? When your flow gets to the pipe at the beginning, because of this presence of the wall and the no slip boundary condition, the velocity at the wall will be 0, right? And there will be a region in which velocity goes from 0 to like 1 to 2, 3, to 3 to 4, and increases until it gets to V infinity, right? And that region is called boundary layer, in which velocity goes from 0 to V infinity, whatever this velocity outside is. These boundary layers, their thickness increases as you go further into the pipe. And at some point, they merge with each other. That location is called the entrance length. Right? And after this location, we have fully developed flow. Velocity distribution looks like this, and it's going to stay the same throughout the pipe, right? And the length of this, we have two main equations. If you go back to your notes, you will see that those two main equations. One equation is only for laminar flow. The other equation is for turbulent flow. Okay. Any questions? No? Moving on. What are the different types of pipe networks? This is something we discussed at the end of our discussion in the pipe flow, on the pipe flows. We have two main types of pipe networks. One was parallel, the other one was series, which is usually the case when you're dealing with this type of. So series is essentially when your pipe's diameter changes, or its shape, or whatever changes. This is a pipe in series. But this one is a pipe in parallel. The idea was, in parallel, your delta P, or your pressure loss of the two pipes, is going to remain the same. But the flow rate, volumetric flow rate, is going to, so total is going to be equals to Q1 over Q2. But in this case, in the series case, your volumetric flow rate is the thing that is remaining constant, and your delta P is the thing that must be added up. If you actually end up in a company that its sole purpose is to do the piping in houses or buildings, all of your analysis will use this basic concept. Okay. Next one. Different types of piping. What is the Moody chart or Moody diagram? And what does it mainly calculate? Do we have anyone? Go ahead.
Show where the pipes turbulent flow and laminar flow. It doesn't show the values of the Reynolds number.
Okay. you're getting somewhere, but that's not necessarily the correct place. So Moody chart gave us the value of friction coefficient inside the pipe as a function of Reynolds number, also the surface roughness. So a Moody chart looks like this. If you recall, we had the friction coefficient, a Reynolds number. For a laminar flow, it was just a line, 64 divided by R Reynolds. And as you move to turbulent flow, these lines change as a function of your surface roughness. It starts from 0 and increase the surface roughness, right? The idea was surface roughness becomes important in the turbulent flow analysis. And it will contribute directly to your friction coefficient. What are the major and minor losses in pipes? Oh no, let me give you a bonus. Yes.
Usually, major losses like when it's turning, when it's like turning in flow, and then like minor losses like along the surface of the pipe.
So major loss is essentially the pressure drop you calculate, right? The major loss is the pressure drop along the pipe that you calculate, but minor losses are the losses that are going to occur because of the fittings or because of the changes in direction inside the pipe, right?
Okay, so minor change in direction, the major ones are because of the system.
Exactly, exactly. Because of the length of the pipe or the fitting or anything or something else. Do we have any questions so far? So these are all the conceptual problems we could get from these chapters. Okay. Let's move on to the other problems. And these like two of them are the problems we have already solved. I just wanted to bring them to your attention, or one of them, problem 3.74. How many do we have? Let's see. Yeah, one of them. This problem 3.74, which is a book problem, is telling us the oil of a specific gravity of 0.83 flows in a pipe shown in the figure below. If viscous effects are neglected, what is the flow rates? Okay. The first thing you need to understand here is that you can, because we are neglecting the viscous effects, you can write the Bernoulli's between the 2 points. So what is the Bernoulli's equation? P1 divided by gamma plus Vs squared over 2G plus Z. And V1, Z1 is equals to P2 divided by gamma. It has different forms. 2G plus Z2. The elevation doesn't change, so this goes away. And okay, if you look at the type of the points we have, and point 1, if you have the, let me draw the shape. Okay. You have this pipe going in like this, and whatever going on here, and you have it in front of you. This is point 2. This is point 1. If you recall from the pitot tube discussion we had earlier, this type of pipe brings down the velocity to 0 isentropically. That's how we measure the total pressure. So velocity at 1 is actually 0, right? And what do we want to calculate? We want to calculate the flow rate. And the velocity at 2 is going, this measurement is going to give us the static pressure. So the total pressure, stagnation pressure, and the static pressure. So for 1, we're going to get the total pressure. This is 0. And here we're going to get the static pressure. And this is going to give us the velocity that we can use to calculate the flow rate. I mean, we can use any velocity to calculate the flow rate, but yeah. And so this V2 over 2G is going to equal to PT minus PS divided by gamma, right? How can we calculate PT minus PS? We have the system of the pipes there. We have to use that pipe system. And we are given all the lengths over there, right? Let me actually, this is something we had in exam 1, very similar to this. Okay. This is the shape. We have a different fluid inside here. This height is 4 inches. So to find the P1 minus P2, we just have to move along this pipe, right? The only points that we can take away from this is that this point 3, the pressure here and here are the same. And also, we can have the same conclusion for this point 4. Okay. Well, what is the relationship between P4 and P2? You are moving down, so your pressure is increasing. Let's call this height H, right? So P4 is going to be P2, or you're moving down, so you just have to add to your pressure plus gamma H equals to P2. What about this P3? P3 plus gamma, let's assume this length is L, plus gamma L is equals to P1. So the only other thing we need to find here is the relationship between these two, right? And the relationship between these two is actually going to be the pressure difference between these 2 points. So since we are moving down from this P4, your pressure is increasing. That's gamma of, I think it's type of oil, multiplied by 4 inch is equals to P3. You plug in all these equations for P4 and P3, you will find the relationship between P1 and P2. Is this clear? Do you remember this? Because we had a lot of people who struggled for these type of calculations. So if you have a question, you should ask now. I mean, you can always send me an email and ask your questions. And you're in a class setting. Your classmates can also use. Okay, so I think if you don't have a question, I guess everyone's clear. Just plug in the numbers. You should be able to do the calculations. And then how do we relate velocity to flow rate? That's Q equals to your area multiplied by velocity. So the area at point 2, right? This area at this point, multiplied by the velocity. That's how you calculate the flow rate. You will also definitely see this type of a problem on your exam. Okay. Okay. So problem 8.9, that's the first problem we want to solve from the chapter 8. It's telling us for a fully developed laminar pipe flow in a circular pipe, the velocity profile is given by this in meters per second, where r is the inner radius of the pipe. Assuming the pipe diameter is 4 centimeters, find the maximum and minimum of the pipe. So if you recall, the idea was in a fully developed pipe flow, your velocity distribution, and this is the general formula, as a function of r is equals to your pressure drop multiplied by diameter multiplied by 16 mu multiplied by the length of the pipe. That's the viscosity. 1 minus 2r divided by d squared. And this part was the maximum velocity, V max, which happens at r equals to 0, right, in the middle of the pipe. What we are given is this. UR is equals to 2, 1 minus r divided by r squared. Okay. So what does this mean for maximum velocity? What is the maximum velocity here? 2. That's it. And what was the average velocity? The relationship between average velocity and maximum velocity was this in a fully developed laminar flow. So your average velocity would be 1 meters per second. Any questions here? No. Okay. So next question, that's 8.17, is a type of question you probably get on an exam. Is the water at 60 degrees Fahrenheit flowed at a rate of 4 gallons per minute through a 6-inch inner diameter plastic pipe. That ID refers to inner diameter. The pipe is 500 feet long and rises a vertical height of 40 feet over the 500 feet. Find the pressure drop. The first thing you need to do is to find the Reynolds number. Right? How do we find the Reynolds number? There are different equations you can use to find the Reynolds number, but all of them go back to the main equation, which was rho v multiplied by diameter divided by mu. We can also write this in terms of your flow rate. If you write it in terms of flow rate, it's going to be 4q pi d nu. And nu here is the viscosity, is the kinematic viscosity, which will be given to you. Okay. We also had another equation for the energy loss of a fully developed pipe flow. That's G multiplied H of L is equal to 128. Gamma L, that's the pipe length, divided by pi d4. And this is for laminar flow, I forgot to mention. So you calculate the Reynolds number first. Then if you plug in the values, you're going to get 1876, which is smaller than 2100. So laminar flow, so you choose this equation for your laminar flow. And you plug in all of the values we already have. Your GHL is going to be equal to 0.03 feet pounds per slug. And then your total pressure loss is going to be equal to rho GHL. This is the head loss multiplied by the gravitational acceleration To transfer it to pressure loss, you just have to multiply it by a density. And your total pressure loss is going to be 0.068 pounds per feet squared. Do you have any questions? Is this all clear? Okay. Is there any other way? Can you think of any other way we can use to do the same analysis instead of using these equations? Because you may forget this equation on your equation sheet, right? Can you think of any other way? We actually had another equation that related all of these parameters to each other. Mass flow rate. What was the equation that was similar to Bernoulli's equation in the pipe flow? That's the head loss equation, essentially, right? So P1 plus 1/2 rho V squared plus gamma Z 1, that's V1, is equals to P2 plus 1/2 rho V2 squared plus gamma Z2 plus G multiplied by your head loss. Okay, if you calculate this head loss, can actually, if you have the head loss or the other, we can use the Bernoulli's mechanical energy equation. It's called the mechanical energy equation. If you don't have any other questions, I guess I will also post this on Blackboard with its solutions for you to go over. So another type of question you might get on your final exam is the other question that we have. That's problem 8.20. I will give you the type of the pipe and also the flow rate. All of those things you need to calculate. And eventually, I will ask you whether this flow is laminar or turbulent. So your final goal would be to calculate the Reynolds number. Any questions? Any questions about the exam? Okay. So let's do this. We have a little more than 15 minutes. And you can use this time to submit your evaluations and send me the receipt for your evaluation. And you can also take a paper out of your notebooks and give me any specific comments if you have. Just write it down on your notebooks. Any specific comments you have about the course or about anything, right? We can do both of them. And let me, whose pen it was? Thank you. I'm going to end the YouTube stream right now. And just make sure to send me your evaluations.